All right, the next test that we're going to take a look at here is a modified version of what we've just practiced in the past two examples. This is the limit comparison test, which is different than the regular or just the comparison test. And really, this limit comparison test is a nice follow-up to the comparison test. Generally speaking, and I have this written down here in the remark, as a matter of strategy, you really want to only use the limit comparison test if direct comparison, or just the regular comparison test, whatever you want to call it, if that fails. Okay? There are some times when you come up with an inequality, and that inequality is in the incorrect direction. So what I mean by this is, let's say you have something like, you have the series of, say, n equals 1 to infinity, and let's say here we have n plus 4 over n to the fifth. Okay, so if you want to do comparison on this, then you could say, okay, let's take the actual series term we have, and then let's say, hey, it would be really nice if this 4 went away. Well, if I get rid of the 4, I get that. But what did I do? If I got rid of the 4, that means I made the numerator smaller. If I make the numerator, and only the numerator, of a fraction smaller, that makes the fraction smaller. So then we effectively get this inequality. I'm just going to write it in a nice left to right way. So 0 is less than or equal to 1 over n to the fourth, which is less than or equal to our given series. So this series here, this series converges because it's a p-series with p equal to 4, which is greater than 1. So this series, it converges, but using the comparison test, direct comparison, that is not enough to show that this series here converges. Why? Well, just because the series of the smaller terms converge, that doesn't mean anything about the series of the larger terms. These terms might be large enough that they diverge. For instance, the series of n, from n equals 1 to infinity. This clearly diverges, and n is definitely bigger than 1 over n to the fourth. So there are series out there that diverge. So the fact that you found a smaller series term and the series of those terms converges, that does not force the series of the larger terms to converge. That is how the direct comparison test can fail, and that's what I mean by your inequality is in the incorrect direction. You really wanted to find a series that was larger that converged, not smaller. So when you find yourself in that situation, such as what we just did here, the limit comparison test is very useful. So the limit comparison test says, if we have two sequences, a sub n and b sub n, they're positive sequences, assume that this limit exists. So you actually want to compute this limit, a sub n over b sub n. Okay, and again, we're going to say that a sub n is our given. This is our given. Okay, so you compute this limit, and then if the answer to this limit is positive, then the two series behave the same way. So if the one converges, then the other converges. if and only if. So they behave exactly the same way. These two cases down here, the L equals infinity and L equals 0 cases, if you're doing everything correctly, you shouldn't run into these two cases. So I'm not going to talk about those in depth. Really, what you should do is always try direct comparison first. And in the event that it fails, such as what just happened here, you then already have your A sub n and B sub n, and then you can proceed to the limit comparison test. And if direct comparison failed, you should not land into these two categories. You should only be in this category. In fact, if you just jump to the limit comparison test and you do find yourself in one of these categories, generally speaking, that means direct comparison you either didn't try, or when you did try it, a not so great choice was made for your B sub n. Okay, so let's actually finish this one off since this is a pretty good example. So we have our inequality. I'll erase that stuff that we don't need. So here's our inequality we found. It was in the wrong direction. So I'm just going to say wrong direction or order. So we already know that this series converges. We already know that. But what we have to do is we have to calculate that limit. So here our A sub n is our given sequence. Our B sub n is our chosen or found series term or sequence. So what we want to do now is calculate the limit as n goes to infinity of A sub n divided by B sub n. Well, if we divide by B sub n, we're really just multiplying by the reciprocal. So now, by the method of dominating terms, if I were to distribute this n to the fourth through, I would have an n to the fifth and a 4 times n to the fourth. So the dominating term is really this n to the fifth. And then bottom, we have n to the fifth. So this limit's equal to 1, which is positive. So we do land into this first case right here. So this tells us that the series of A sub n converges if and only if the series of B sub n converges. This means they behave the same way. They either both converge or they both diverge. And since we know that this series of 1 over n to the fourth converges, this implies by the limit comparison test that our given series, n plus 4 over n to the fifth from n equals 1 to infinity, converges also.